All right, so today's topic is going to be on ellipses. They are introduced, or one of the words you might hear is something called like conical sections. So this comes under conical sections. And there's a reason why we call it that also. But I want to talk about a special shape called an ellipse and some applications of it. So it's not really going to be me working out problems other than kind of explaining the concepts and what they can do. So before I get to the ellipse itself, there's one shape I want to talk about that's closely related to it, which is a circle. So I'm going to start with the circle, and then I'm going to kind of broaden that idea out to what we call the ellipse. All right, so here we have a circle. All right, so this is the most common ellipse, right? This is what we talk about first. Before you even learn what an ellipse is, you all seen a circle. So let's talk about the circle and try to make some connections here. So what makes a circle so special, right, is that every point on this circle is the same distance from the center of the circle, right? That's pretty much how it is explained. Like every point on this circle is the same distance away from this point in the middle, right? And we all say it's the same distance from the center of the circle. Now, if I go from the center of the circle to where this point is, we call that a radius. But if you go through the radius and all the way across to the other side, we call that a diameter. All right. So some of the facts that we tell you is, okay, the diameter is twice as long as a radius, or you'll flip it and say the radius is half as long as a diameter. So there's a couple of adjustments that I want to make to that statement, because only when I make this adjustment will it make sense when I move away from this circle. So this point is equidistant from this center, right? But what I want to call it is a focus. It's an equal distance away from the focus, and the focus happens to be right here in the middle. Notice how I use the word focus. All right, so here we go. Let me click this dot here. And notice how it says I have a radius length of 9 units. Notice no matter how I'm spinning it, right? No matter how it's spinning, this number is not changing. It is locked at that one distance all the way around. That's what makes this a circle. Now, remember, we're not going to call this a center, even though this is the center. We're going to call that the focus, because that's where we're going to focus on. So I'm going to hit that. And as you can see now, I have a dot there called F2. That's for the focus. All right. So from the focus to the point on the circle, right, that's called a radius. See that? So it's a radius, and that radius is not changing. The radius is not changing. All right. All right, so here's where it gets a little bit more interesting. So let me shrink that just a little bit, and I'm going to change this. Watch what happens. Okay, now I have an ellipse. You see that? Now we're talking about something that's more of an oval shape. Now look what happened here. Now as I spin this radius around and around and around, right? From the center, look what's happening. Now these numbers keep changing. They get big, and right here they get small, right? Then it gets large again, and then they get smaller again, and then they get large again. Because as you can see, the radius is at its biggest along this horizontal, then it's at its shortest here. So it keeps going up and down between those two numbers. So that number keeps changing. But remember, in the circle, as we spin things around, there was a number that stayed the same. So because we went from the focus to the edge of the circle, what's so special about the ellipse is it doesn't have one focal point now. So it has two focal points. And so it's not really about the center to the edge of the curve. It's really more a relationship between the focal points and the edge of the curve, all right? That's where we got to start making the connection, and that's where the ellipse comes in very handy. All right, so I'm going to stop moving this thing around, let it stay in place. And what I have to get rid of right now is I'm going to get rid of that radius because that's not really what I want to pay attention to. What I want to do is connect this point to both focal points. We call that a foci. F-O-C-I, foci, plural for focus. All right. So now this is the crazy thing about it. Now, if I add this up with that up, it's going to always give me the longest distance. So with a circle, we call the part that cuts all the way through straight down the center the diameter, right? And no matter if I go up, down, left, right on the circle, the diameter is always the same. But on an ellipse, if I think of what the word diameter means, it wouldn't be the same up and down, left and right. Notice right here, this is shorter, but right here, this is longer. So we changed the vocabulary up just a little bit to distinguish between the two. We call this the major axis, and this one is the minor axis. All right. Major axis, minor axis. So whichever one is the longest is your major axis. Whichever one is the shortest is your minor axis. Now, when we cut that in half, we call that a semi-major axis, and we call this a semi-minor axis. All right. So those are the vocabulary that we use when we start describing parts of an ellipse. So there it is. I'm going around and around and around. I'm adding up these segments, and it's giving me 30 every single time. So I really want to start talking a little bit more about these focus points, because these focal points can do some really cool stuff. So remember, when we talk about a circle, it's just a special case of an ellipse. So if I bring this in, see what's happening? See how an ellipse is going to have two focus points? A circle is when those two focus points actually land on top of each other. Now we're talking about a circle. All right. That's how it works. That's the relationship right there. So it still has a focus point, just one instead of two. So applications of ellipses. Number one, we use ellipses when we study planets and orbit systems, all right, and how things orbit each other. That's one of them. The second one, they have applications to light and sound. Light and sound. You can study light and sound, and you can do some really cool stuff using ellipses. In the medical field, I just found out that ellipses are used to pulverize kidney stones, all sorts of stuff. So I'm gonna go into each of those so that you can kind of see an example of how that works. All right, so there's another word that I didn't use yet. We call that eccentricity, right? Eccentricity. If eccentricity hits the number 0, that lets me know that my orbit or my shape is perfectly round. As I get closer and closer to 1, it lets me know that whatever my shape is more elongated or exaggerated, right? So Earth's orbit around the sun is pretty close to 0, which means it's almost perfectly round, right? That's how we orbit around the sun. Not perfectly round, but close to it. Now, right out here, Halley's Comet, it has an eccentricity closer to 1, which means we know that it's stretched out. It's way more oval shaped than what our orbit does. That's why Halley's Comet shows up once every 76 years. I think the last time it was sighted was around 1986. I remember when that was in the news, but I never did see the comet myself. So if you're going to make it add 76 plus 1986, if you think you're going to be around at that time, start watching for the skies. Another cool thing about this focus point, remember what I said, when you have something that's elongated, you're going to have two focal points. So just imagine the sun being at one of the focal points, and there's some imaginary point in space where this other focal point lands, right? That's what creates, or that's what controls the shape of our ellipse itself. So it's really cool that, people were able to kind of, from the ground, look up, study the relationship and the distances and stuff, and be able to make accurate predictions on orbits and when things will show back up. And it's like clockwork. The original clocks aren't the ones that you put on your wristband. The original clock is the orbit itself. All right, so here's the medical application of lithography. I think that's how it's pronounced. It's a weird word, but this is how we eliminate or destroy kidney stones. So we locate the kidney stone in the patient. They lay them on a special bed or water cushion, and this device right here we place against them. So using our medical technology, we can locate the kidney stone here. Now this is elliptical shape. Now remember, an ellipse has two. It has two focus points. So one of them is here, and that's where the shock waves are sent. So it's like a sound. It's like ultrasound or something like that. So it sends a sound, and the sound waves start bouncing around inside this ellipse, but it focuses in onto the other one right there. So with accuracy, the mathematics is finding the exact location of the focus points. Once you do that, it's easy. You just set it up, turn it on, and you let the numbers do what they're supposed to do. And they are going to do exactly what they're designed to do, which is to take from one focus, bounce off, and really zero in into that. So it's almost like, because when you're dealing with sound, depending on the shape of the room, the acoustics of it, right? What happens is the sound goes and it spreads all over the place and it bounces off of walls. It does all this weird stuff, right? But when you use an ellipse, you can really control that. So it's almost like taking light that spreads out in all directions and turning it into a laser. You get what I mean? So now we're talking about really like targeting our sound to one focus point that can be used to vibrate, because that's basically what's going to happen. You're going to vibrate that kidney stone until it breaks apart. It's like creating an earthquake, a very small earthquake at a very particular point, because these kidney stones, I was told, are extremely painful. I'm talking about when you're using the restroom, blood, like it is very painful, enough to like sit you down and lay you down where you don't want to move. I knew a guy that had kidney stones, and when he was explaining it to me, I knew I didn't want any parts of it. So sometimes this is hereditary. I'm going to just say drink a lot of water, because dehydration is one of the things that can get you kicked off with a kidney stone. But we can use ellipses. All right, here's another one. This is with the sound now. So like, this right here is like a diagram of the shape of the metro in Paris, right? So it's like an elliptical shape. So based on where you're standing, you can literally talk. The sound will bounce off and focus in on the other focus point. And you can have a conversation with the person across the room. Like I'm talking about 40, 50, 60 feet away. Speak at a regular tone, right? And without hollering. And it'll go right to their ears. And it's almost like they're standing in front of you. And the crazy thing about it is nobody else will hear that conversation. But you two have to stand on the focus points, and then only you two can hear what's being said. So with the sound, it can do some really cool stuff. We call these whispering galleries. I was actually in New York City, and I've been to Grand Central Station before. And come to find out, I did not know this at the time, but they have whispering galleries at the Grand Central Station. All right, so this is kind of how the whispering gallery looks. I'm going to click out to some more pictures. Notice these are elliptical shapes. See what I'm saying? The half of an ellipse. And if you pay attention, there's people standing in the corner. So you could stand in this corner and go to the other corner across from it and just start talking. And whoever's standing in that corner will actually hear everything you're saying without disrupting everybody else around, because it takes that sound and it focuses in on a focus point. So yeah, they had that in New York City. And if you just see people standing in the corner, don't laugh at them. They're probably just testing it out just to see if it works. But it does work though. But I've been to Grand Central Station and I never knew that. So I'm going to use my computer to kind of show what the light or the sound waves can actually do and why these focus points are what they are, right? So like as I move this point around, it's just going to freeze it, all right? So notice how I'm freezing. And no matter what, pay attention to where these lines are all focusing in on. So just imagine if this is light or if this is sound, right? Being radiated from this one focal point, and it bounces against any point. Any point around here is just going to bounce against it, and it's going to come right back in and land in one spot. Notice it doesn't go anywhere else. That's what we mean by it can target. You get what I'm saying? We can target it. We can focus in. With light, we go from light to lasers, right? And with sound, we talk about sound to like ultrasound, right? It's ultra. It's like really, really concentrated now. So it's kind of cool how these ellipses work. And you can see just by how dark it's getting right there in that one area that it's all focusing in one place. So if I go all the way around, you see what I'm saying? Boom, focus point, focus point. Like this is how headlight works. You know, you have a bulb that sits inside of something that's a little conical. And then when the light shines, it just shoots one direction and then it gives you better light. That's what we use for all sorts of stuff. So ellipses have all sorts of uses, but you just got to understand, you know, there's numbers behind it and there's reason why these things work. Well, I hope that kind of sparked your interest in this topic of ellipses. Maybe tomorrow I might do a problem where we just kind of find a semi-major axis or locate a focal point or something like that. But I just kind of wanted to go into what ellipses are and some of the cool stuff that they can do.